start off easy. We're going to look at detection in the absence of noise. And then we're going to start talking about what happens when noise gets introduced. And then in order to talk about what happens when noise gets introduced, we have to go back to what we were talking about last class and the class before with random processes. Okay, detection. So the main idea, let's go back to the hardware model. We have physical layer access. Followed by an amplifier. Followed by addition of noise. Then I actually don't think I put this in the original version, but I should have. Prior to analog to digital, we should do a low pass filter. And we do a low pass filter to ensure that there are no high frequency components that cause problems with sampling. Okay, low pass filter, and then analog to digital. Then detection. Detection, actually let me elaborate on this a little bit. Detection consists of a linear filter. Let's say it has impulse response H of K. Some kind of decision device. So the decision device will examine the output of the linear filter and decide whether it's a 0 or a 1, whether a 0 or a 1 is sent. So basically, all of this stuff, we will talk a little bit about the low pass filter. We care about the noise, obviously, but as far as things we can design are concerned, we're only concerned about this end. So from the analog to digital, we have some sequence that I'm going to call Y of K. This gets passed through the linear filter. Then conventionally what we do is we convolve Y of K and H of K. And then we will examine it at multiples of the sample time. So in other words, we'll let that filter run, and then at multiples of the sample time, we'll take a look at the filter output. And then the decision device, at each multiple of the length of a bit, will decide, based on the output of that linear filter, we'll decide whether that bit is a 0 or a 1. So the easiest thing to do is let's start by looking at the problem without noise. So the detection problem without noise is trivial. But what I'm going to do, basically what you can do is just look at any individual sample and you'll be able to tell whether that bit is a 0 or a 1. But what I'm going to do is I'm going to set up the problem by designing the detector, designing the linear filter exactly as I would if noise were present, and the decision device as though noise were present, and then later on we'll see how this changes when we have noise. So, we have channel observation. Y of K is passed to the linear filter. With impulse response. H of K. So the decision device examines the filter output at time, let's call it J and B, to decide the jth bit. So remember a second ago, the jth bit is transmitted between j minus 1 NB and j NB. The samples j minus 1 N times NB to j times NB. So in other words, once the jth bit is sent, at that time the decision device makes its decision. So drawing a little diagram, here's the jth bit. It's transmitted between j minus 1 NB, j NB. And it's this is passed through the filter, and it's at this time that the decision device operates. So once that happens, at time j and b, this decision is made, and then what we get is, I'm going to call it b hat of j. I call it b hat because it's not necessarily equal to bj. It could contain an error, but it's the detector's best estimate of what the bit was. Alrighty. So let's write some of this down. Some more definitions. Let by j be the random process, or excuse me, be the discrete time function representing the filter outputs at time j and b. So the notation I'm going to use for that is square brackets. What is the filter output? It is y of k involved with h of k. And the notation for evaluated at time j and b, I'm going to use square brackets, subscript j and b. So this is what 5j is. Decision device we'll see why in a second in the noise-free case, but in the case with noise it also works, and we'll probably see that either later today or next class. The decision device implements a threshold test. So let's let that function be d. Actually, let me just describe how it works first. So let's let there be a threshold z, so that if phi of j is greater than z, greater than or equal to z, then decide 0. And if phi of j is less than z, then decide 1.